Starting this first chapter, we looked into the definition of a pure substance. We defined the pure substance as a substance which has uniform composition throughout the material. Then we looked into phases. We defined different phases. The definition of the phase being the uh, substance having a particular molecular arrangement or atomic arrangement having distinct boundaries. And then we looked into solid, liquid, uh, gases as the primary phases, and then there are secondary phases within a primary phase. And we identified that liquid to vapor phase transformation is probably the most essential phase transformation as regards to the thermodynamic processes involved in mechanical engineering. We'll begin with the phase change process of pure substance, which involves the liquid to vapor phase transformation. So liquid vapor phases and their mixture, they need to be understood in detail. So we'll understand the process of phase transformation from liquid to vapor, and for that we have taken the example of water as the test case to set the basic principles involved, and all pure substances would then exhibit the same generic behavior, that of water. So we said that, let's say we have a piston cylinder device which contains water at, here is it, water at 20 degrees centigrade and 1 atmospheric pressure. What is the state or what is the phase of water at this condition?
Liquid, sir.
It is essentially liquid. And we refer to this water as compressed liquid or subcooled liquid, which means a liquid which is not about to vaporize. That is basically a compressed liquid, like you have over here. Pressure equals to 1, temperature equals to 20. You have liquid state and you have a heating source at the bottom. This is your state 1, which is being defined as the compressed liquid state or the subcooled liquid. Now, if I add certain amount of heat into this material, let's say if some heat is added to this container such that the temperature goes to 40 degrees centigrade, what would happen in that case?
Volume
Expansion
increase.
take place, sir.
Expansion would take place. That means if the temperature would go up, the specific volume would also go up. Isn't it the case? Specific volume is what?
The
Volume,
volume per unit mass.
volume per unit mass. And since the mass is constant, if the volume is increasing, the specific volume would also go up. Clear enough?
Yes, sir.
Yes, sir.
All right, but the phase of your material under study, phase of water would be what?
Liquid, sir.
It would still be liquid. That means that if heat is transferred, to the water so that the temperature raises to, let's say, 40 degrees centigrade, the liquid water would expand, and as the result of its expansion, the specific volume would increase. To accommodate this increase, the piston would move slightly up, and the pressure in the cylinder. Numan, kindly stop sending me the messages, please. If the pressure would, if the expansion would take place, the pressure in the cylinder would still be 1 atmospheric, since you have no extra pressure. The outside atmospheric pressure is 1 atm and the weight of the piston has not changed. So even though this moves upwards, the pressure within the cylinder would still be 1 atmospheric, and the water would still be categorized as compressed liquid because the water has not started to vaporize yet or is not about to vaporize. Is this point clear?
Yes, sir.
All right. Now, if we take the temperature to 100 degrees centigrade, how? By adding up heat. So I am transferring heat to the system until the system reaches to the temperature of 100 degrees centigrade. At this point, the water is still a liquid. But if I add little more heat, any heat addition, what will it cause?
Vaporization.
Vaporization. This would result in the liquid to vaporize. That means the phase change process would initiate, and we refer to such a liquid which is about to vaporize as saturated liquid. So this is your state 2 where you have increased the temperature to 100 degrees centigrade. The pressure still is 180 m and the specific volume has increased. This is your state 2, but within this container your water is still in the liquid form. Such a liquid where a small amount of addition of heat would convert it into vapors is referred to as saturated liquid. So this liquid at state 2 is basically referred to as saturated liquid. Clear so far?
Yes, sir.
All right, let's move ahead. So we continue adding heat. That means the boiling starts, but the heat added would not cause any change in the temperature. Temperature would stop rising until and unless the liquid is completely vaporized. That is, the temperature during the entire phase change process would remain the same if the pressure is held constant. Let's say we are somewhere down the vaporization line. We have completed half of the vaporization process. That means half of the liquid has vaporized, and now in the container we have equal amounts of liquid and vapor. So if you have equal amounts of liquid and vapor, the first thing is your specific volume would have increased, temperature and pressure remains the same, and your state is basically state 3. Now if you continue heating, you would reach to a point where the vaporization process has completed and the last drop of liquid also gets vaporized. This is your state 4, where you are still at the same pressure, which is 1 atmospheric, and the temperature is also the same, which is 100 degrees centigrade. But now in all the container that you have the vapor phase. Clear? Let's say I extract some heat out of this container. What would happen if I extract some heat out of this container?
Condensation.
Yes. So any heat loss from this vapor will cause the vapor to condense. And a vapor that is about to condense is called saturated vapor. So this state 4 is basically the saturated vapor state. And if you recall the state 2, all the states between state 2, which is saturated liquid, and state 4, which is saturated vapor, are called saturated liquid vapor mixture, where the liquid and vapor phases coexist in equilibrium. So closer to state 2, you will have more liquid, and closer to state 4, you will have more vapors. Clear enough?
सर एक क्वेश्चन है।
जी जी।
सर ये हम कह रहे थे कि 40 डिग्री सेंटीग्रेड पे सिर्फ लिक्विड फेज एग्जिस्ट करता है। सर
जी।
जो इवेपोरेशन है वो तो स्पॉन्टेनियस प्रोसेस है ना, तो क्या जीरो वाटर वेपर्स होंगे उस कंटेनर पे?
उस वाटर
हीट
उसके
ऑन
ऊपर
हीट।
जीरो वाटर वेपर्स होंगे, मतलब वाटर वेपर्स जो एग्जिस्ट कर रहे हैं कंटेनर के अंदर की बात कर रहे हैं, कंटेनर के अंदर कोई वाटर वेपर्स नहीं होंगे।
ओके सर।
ठीक है। इफ इट इज ओपन टू एटमॉस्फेयर तो कंडीशन डिफरेंट है, लेकिन अगर आप क्लोज कंटेनर की बात कर रहे हैं तो थर्मोडायनामिकली कोई वाटर वेपर्स नहीं होने चाहिए। क्लियर?
ओके सर। ओके सर।
Now, moving on, if you continue adding heat, what would happen? You would again, if you continue adding heat, you would again enter into a single phase region. Once the phase change process is completed, you would enter again into the single phase region. This time, the phase which you will be having would be which phase?
वेपर सर।
वेपर फेज पे।
Vapor phase, obviously. That means any further transfer of heat would result in increase in both the temperature and the specific volume within the system. So let's say if I have increased the temperature to 300 degrees centigrade, the temperature that I have increased is I have increased the temperature to 300 degrees centigrade. Now, this is my state 5. This is state 5 where I've increased the temperature to 300 degrees centigrade. Pressure is still 1 atmospheric within the container. Now, this is all vapors within the container. If I take small heat out of these vapors, what would happen?
वेपर्स ही रहेंगे सर।
It would still be vapor. The only thing would be that the temperature would drop and the specific volume would decrease, but no condensation would take place unless and until you get back to 100 degrees centigrade. Clear enough?
यस सर। सर एक क्वेश्चन है
So
सर।
just give me a minute. I'll come back to that. Just give me a minute. So a vapor that is not about to condense or which is not a saturated vapor is basically called superheated vapor. This vapor would be called superheated vapor. Is this point clear?
यस सर।
All right. Now जी आप पूछिए सवाल।
सर ये जो वेपर्स कंडेंस होंगे वो अगर 100 पे होगा टेम्परेचर, उधर से हीट निकालेंगे तो फिर ही होगा, उससे ऊपर नहीं होगा ना?
उससे ऊपर नहीं होगा।
ठीक है सर।
ठीक हो गया। Now this would become more clearer if we move on towards the schematic and try to represent the same process that we have seen onto a temperature specific volume plot. So temperature specific volume plot would give you how did the states change during this process. The process started with the first state. The first state was what? State 1 was what? Your water was at 20 degrees centigrade
लिक्विड
and it
सर।
was liquid and it was 1 atm pressure. So let's say I have this point which indicates my temperature and some specific volume V1 to which it corresponds. I started heating up the system, and as I heated up the system, my temperature and the specific volume both increased. So I went to state 2. This is my state 2 where I took my sample from my system from 1 to state 2, which is 100 degrees centigrade. At 100 degrees centigrade, then we defined the state 2 was 100 degrees centigrade liquid. State 3 was what? Again 100 degrees centigrade. You have 50% liquid and 50% vapors. So this is your state 3. Your specific volume is increasing, but your temperature is still 100 degrees centigrade. At state 4, you have 100 degrees centigrade and you have all of it as vapor. So 100% vapors. This is your state 4 where you still have all of it as vapors, temperature is the same, and state 5 is where you have the system at 300 degrees centigrade and still as 100% vapors. Now if you combine the line, you have such a process that is taking place. In this process, your point 2 is basically saturated liquid. Is it clear? This point 2 basically corresponds to saturated liquid state. Clear enough?
Yes, sir.
And the point 4 basically corresponds to saturated vapor. From 1 to 2, you have compressed liquid region. And from 4 to 5 or in 2 to 4, you have saturated mixture. Mixture of what?
Sir, vapor and liquid.
Yes,
Liquid and
saturated liquid vapor mixture. And from 4 to 5 you have superheated vapor, and all of the process is taking place at 1 atmospheric. This is very important. Your process is taking place at 1 atmospheric. So this is a constant pressure line. Clear
एक्सक्यूज मी
enough?
सर, लेकिन अगर हम किसी चीज को हीट करते हैं तो उसके अंदर जो सा ये जो सिलेंडर है उसके अंदर सर ये जो से ओए सर ये जो से अगर जो हमारा ये सिलेंडर है इसके अंदर अगर हम उसको हीट कर रहे हैं ना तो उसकी वजह से मॉलिक्यूल्स की एनर्जी बढ़ रही है, तो उसकी वजह से प्रेशर बढ़ना नहीं चाहिए।
अगर आप अपने पिस्टन को मूव नहीं करने देंगे तो वो बढ़ेगा। अगर आपने पिस्टन के ऊपर कोई प्रेशर नहीं रखा हुआ तो जितनी आपने हीट दी है वो कहाँ पे जाया होगी? वो
वर्क डन में।
वर्क डन में। बिल्कुल, वेरी गुड। उसका स्पेसिफिक वॉल्यूम जो इंक्रीज हुआ है वो इसी वजह से हुआ है। क्लियर?
ओके सर, थैंक्स।
Alright, moving on. Now you have looked into the process of phase transformation. Basically this temperature, the isothermal temperature, which is 100 degrees centigrade in this case, it is the saturation temperature at 1 atmospheric pressure. That is the phase transformation temperature at 1 atmospheric. This temperature is known as T saturation. So what is T saturation and temperature and T saturation pressure? The temperature at which water starts boiling depends upon the pressure. If the pressure is fixed, so is the boiling temperature. If I fix the pressure to 1 atmospheric, the boiling temperature would be 100 degrees centigrade. Clear enough?
yes, sir.
Different temperatures at different temperatures. If I have different set of temperatures given to me, each temperature would have its own saturation pressure. That means if I say 15 degrees centigrade, at 15 degrees centigrade, you need to have a pressure of 1.71 for the boiling. This is the pressure kilopascal that would be required for the boiling process, or this is the saturation pressure. Water boils at 100 degrees at 1 atmosphere. Saturation temperature, what is saturation temperature? It is the temperature at which pure substance changes phase at a given pressure. So if you have fixed the pressure, your pressure is fixed. For that fixed pressure, you will have some saturation temperature or some boiling temperature. Similarly, you have saturation pressure. It is the pressure at which pure substance changes phase at a given temperature. So if you have fixed your temperature, you would have certain value of pressure, which is P saturation, at which your system or substance would start boiling. Clear enough? Or start changing its phase. Is this point clear?
Yes sir.
All right, and for water, the liquid vapor saturation curve of a pure substance is given like this. This indicates that if I increase my temperature, the boiling pressure or the pressure at which phase transformation would take place would also increase. So if I raise my temperature to 100 degrees centigrade, I know that the boiling would take place somewhere at about 101 kilopascal. Clear enough? Now, the latent heats are the heats associated with phase change process. That means it is the energy absorbed. It is either the energy absorbed or released during a phase change process. Latent heat of fusion is the energy required for melting or energy absorbed during the melting process, and it is equivalent to the energy released during the freezing or solidification process. You may not encounter latent heat very often in thermodynamics of mechanical engineering. However, the latent heat of vaporization would be the energy that you'll be looking into very frequently. It is the energy absorbed during the vaporization process, or it is equivalent to the energy released during the condensation process. And the magnitudes of these energies would depend upon the temperatures or pressures at which the phase change process is taking place. For instance, at 1 atmospheric, the latent heat of fusion for water is 333.7 kilojoules per kg, and the latent heat of vaporization, which should be more, is around about 2250 for water. Now, why do you think, or do you know that it takes longer time to cook at higher altitudes?
Yes, sir.
Yes sir.
Yes sir.
Why is it so?
सर प्रेशर उधर लो
सर
होता है
प्रेशर डिक्रीज हो जाता है।
एटमॉस्फेरिक कम होता है जिसकी वजह से बॉइलिंग जो जल्दी स्टार्ट हो जाती है और उस वजह से जो हीट होती है, हीट एनर्जी
सर बॉइलिंग
खाने के
पॉइंट
लिए
इंक्रीज हो जाता है जब प्रेशर लो होता है तो
Who is this?
बल्कि सर डिक्रीज होता है, डिक्रीज होता है सर।
Yes, you have just seen the curve. ये क्या है? यही बता रहा है कि जैसे जैसे आपका प्रेशर इंक्रीज हो रहा है, let's say if you are at 400 kilopascal, your boiling temperature would be somewhere around 160, 170, or sorry, 140, 150 or 135, somewhere around that. So जैसे जैसे आपका प्रेशर बढ़ रहा है, आपका बॉइलिंग टेम्परेचर जो है वो बढ़ रहा है, और जैसे जैसे आपका टेम्परेचर कम हो रहा है, as your temperature is decreasing, as your pressure is decreasing, your boiling temperature is also decreasing. Clear? So the atmospheric temperature, atmospheric pressure, and thus the boiling temperature decreases with the elevation. That means if I am at 20,000 meters height from sea level, the atmospheric pressure is 5.53 and the boiling temperature is 34.7 degrees centigrade. So imagine the amount of heat would be required to reach 34.7 degrees centigrade as compared to 100 degrees centigrade. This amount of heat for 34.7 would be very less as compared to at 100 degrees centigrade. So once you are at altitude, higher altitude, your atmospheric pressure is low, your boiling temperature or T saturation is low, and if the T saturation is low, you would have to cook for longer time to provide the same amount of heat as it is required to reach to 100 degrees centigrade. Clear enough? That's why it takes longer.
एक्सक्यूज मी सर।
जी जी
सर इस पॉइंट को दोबारा करते हैं।
मैं बता देता हूँ
सर। मैं कह रहा था कि जब नहीं सर, बॉइलिंग टेम्परेचर जब रीच हो जाता है तो सर लिक्विड जो है फेस ट्रांसफॉर्म होकर उसका वेपर में कन्वर्ट हो जाता है। तो सर अब अगर हम सपोज 34 डिग्री पे हमारा जो है ना वेपर में चेंज हो रहा है, तो उसके बाद लिक्विड का अपना टेम्परेचर तो इंक्रीज नहीं हो रहा होगा, तो हम कुकिंग को जो है ना ज्यादा देर करके कैसे उसको कर सकते हैं? हीट तो उसको उतनी प्रोवाइड होगी ना, बाकी तो उसमें कन्वर्ट होना शुरू हो जाएगी वेपर्स में। यस सर।
हाँ जी, और बताइए।
सर लेटेंट हीट अब जैसे जैसे हमारा प्रेशर डिक्रीज हुआ है और टेम्परेचर भी रिलेटिवली हमें उतना ही लेस चाहिए होगा बॉइलिंग रीच करने के लिए। सर अगर टेम्परेचर
ये ऐसे ही है कि लेट्स से टू गेट टू 100 डिग्री सेंटीग्रेड you need this much amount of heat. To from this level you need to get to 100, you need this much amount of heat. For 34.7, let's say you get to 34.7, by providing this much amount of heat. तो किस में हीट ज्यादा गई है?
सर 100 वाले में हीट ज्यादा गई है
जी, तो जब तक आप इसको उतनी हीट नहीं, उतनी देर के लिए नहीं कुक करेंगे ना, इफ द हीट इज मोर, वन थिंग इज you provide more heat and less time. The other thing is you provide heat for a longer time so that the food gets cooked thoroughly. That's the difference.
सर एक्चुअली मैं लिक्विड की बात कर रहा हूँ सर लिक्विड जो है जब फेस चेंज होता है तो लिक्विड
जी
का अपना टेम्परेचर तो उतना ही रहता है ना बाकी जो एनर्जी होती है वो तो वेपर्स में ट्रांसफर होना शुरू हो जाती है सर
लिक्विड
सपोज सर हम पानी बॉईल कर रहे हैं 100 डिग्री सेल्सियस पे जाके पानी बॉईल होना शुरू होता है सी लेवल पे तो
जी
उसके बाद जो लिक्विड है उसका टेम्परेचर 100 डिग्री पे ही रहेगा बाकी जो एनर्जी हम एक्स्ट्रा हीट के जरिए दे रहे हैं वो उसमें खर्च हो जाती है जो हम फेस ट्रांसफॉर्म कर रहे हैं या फिर आगे स्टीम का अपना टेम्परेचर इंक्रीज होना शुरू हो जाता है लेकिन लिक्विड जो है ना 100 डिग्री को नहीं छोड़ता वो उसी पे रहता है तो मैं कह रहा
जी
हूँ सर
जी
जब हम हायर लेवल पे जाएंगे तब भी बॉइलिंग
जी
इसी तरह होगी तो अगर हम कोई चीज पानी में जिस तरह आप कह रहे थे कुक कर रहे हैं तो हमें ज्यादा टाइम के लिए कुक करनी पड़ेगी लेकिन उसको हीट तो उतनी मिलेगी ना सब्सटेंस को 34.7 ही वाटर की अगर हीट है तो उतनी ही
जी
सब्सटेंस को हीट मिलेगी तो कुक करना तो उसको फिर भी मुश्किल ही होगा मैं ये कहना
नहीं,
चाह रहा था सर
अच्छा एक मिनट। आप दो चीज़ें इसमें, अब इसमें आप हीट ट्रांसफ़र को भी लेके आ गए। एक चीज़ ये है कि आप हीट कितनी देर के लिए दे रहे हैं, एंड द सेकंड थिंग इज़ फॉर हाउ मच हीट यू आर गिविंग इन। अगर आप हीट कम दे रहे हैं तो नॉर्मली यू टेक लॉन्गर टाइम टू कुक, ऑलराइट। अगर आप हीट ज़्यादा दे रहे हैं तो इट टेक्स relatively lesser time to cook, number one. Number two, it is also related to the amount of water that you have at 100 degree at 34.7 degree centigrade. आप ये कर रहे हैं, let's say you're dragging it away, but anyways, if you have this container and you have water in it, let's say, and you have some potatoes in it, all right, you are giving it the heat. Now from room temperature to 34.7 degrees centigrade, you have given certain amount of heat to the system. The water is still not boiling, all right. The water has started boiling.
Yes,
now the extra heat would be acquired by these potatoes and the water to evaporate. Clear enough?
yes sir
So the amount heat input to the system is what? Less or more than 100 degrees centigrade?
sir lesser.
All right. So if the heat, अगर इस सिस्टम में हीट ही कम आई है तो क्या कुकिंग प्रॉपरली हो जाएगी?
नहीं सर
लेकिन अगर ये थोड़ी हीट ही लेट से मैं 2 घंटे के लिए देता रहता हूँ तो फिर क्या होगा?
सर स्लो कुकिंग प्रोसेस स्टार्ट
हो जाएगा और अल्टीमेटली
Yes.
कुकिंग होगी ही होगी. Yes,
सही
you
है
may
सर
say that the water may evaporate away, but if the water evaporates, you will keep on adding the water. Clear?
सही है सर समझ गया सर
In case of
Thank you.
100 degrees centigrade, if you have placed in the potatoes, so to keep the water to take the water to 100 degrees centigrade, you have already supplied this much amount of heat to the system, which would have been consumed by the potatoes. So the heat
Yes, sir.
input to the system is more, heat input to the system is less when you are at different temperatures. Clear?
सही है yes sir thank you sir.
Welcome. All right. Is the elevation concept clear to you?
Yes, sir.
clear.
Yes, sir.
All right. Moving on, some of the consequences of saturation temperature and saturation pressure. It is important to understand that you have certain uses of these saturation pressure and temperature. Saturation temperature and pressure. Number one is that let's say I have this test chamber with me. This is the chamber and I am doing some experiment that needs to be performed at minus 196 degrees centigrade. In order to keep the temperature of this test chamber to be at minus 196 degrees centigrade, what I'll do is that I'll insert it in another chamber which contains liquid nitrogen. Liquid nitrogen basically exists at minus 196 degrees centigrade. That means at minus 196 degrees I can have liquid nitrogen, but at 25 degrees centigrade I should have liquid nitrogen or gaseous nitrogen?
Gaseous
Stable
nitrogen.
phase. All right, very
Gaseous.
good, very good. So if I have somehow contained this liquid nitrogen over here and I have opened this container to the atmosphere, what should happen? Liquid nitrogen should convert from liquid phase to
Vapor phase.
Vapor phase.
gaseous phase or the vapor phase, because this is an opening which says the outside pressure is 25 atmospheric, so liquid nitrogen should evaporate to acquire the stable state at 25 degrees centigrade, which is the gaseous state. But uh, where would this heat come from? In order to convert from liquid to gaseous phase, you require heat. Where would the heat come from?
सर एटमॉस्फेयर के गैसियस पार्टिकल से फ्यूजन।
Sorry?
सर एटमॉस्फेयर के अंदर मौजूद जो गैसियस पार्टिकल होंगे उनकी काइनेटिक एनर्जी से ये वेपराइजेशन होगी।
All right. You have this test chamber. Test chamber बाहर से heat absorb कर रहा है. Where would this heat go?
सर अगले चेंबर में आ जाएगी।
This would go to liquid nitrogen. Liquid nitrogen, since this liquid is not the stable form of nitrogen, it would take the energy from the test chamber and would evaporate by taking up the heat from the test chamber to convert it to the stable form, which is the gaseous form. Thereby the test chamber would essentially remain at minus 196 degrees centigrade. So whatever experiment I have to perform at minus 196 degrees centigrade, I'll be able to perform, because any heat transfer from the surroundings to the test chamber would ultimately be transferred to the liquid nitrogen, which would take up that heat and evaporate into the atmosphere. Clear enough?
Yes, sir.
Yes, sir.
All right. All right. Similar is the case with where you, I don't know whether you have been through that or not. Normally, skin specialists, there are certain defects on your skin, marks on your skin that needs to be removed. And if you have been through a skin specialist, they use liquid nitrogen to remove those marks or uh, those what do you call those protrusions on a human body. Uh, they are normally being removed by liquid nitrogen. Have you ever seen that? Have you ever observed that? Or have you ever been through that? जो बॉडी पे मार्क्स होते हैं,
Yes, sir.
अगर स्किन स्पेशलिस्ट पे जाए के पास जाएं तो दे यूज लिक्विड नाइट्रोजन टू रिमूव देम. You know how?
ये नहीं पता सर.
All right. What happens is that liquid nitrogen, what they do is that they soak or they dip a cotton swab in liquid nitrogen. Now, the liquid nitrogen, as soon as it comes to the atmosphere, it should be in which form? Gaseous form.
Yes, sir.
At 25 degrees centigrade, liquid nitrogen should convert from the liquid phase to the gaseous phase, because gas is the stable phase. So liquid nitrogen, cotton swab dipped in liquid nitrogen should convert to the gaseous phase. What they do is that they bring this cotton swab, which is dipped in liquid nitrogen, to come in contact with the human body, where there is that mark or spot that needs to be removed. As soon as this swab comes in contact with the body, the liquid starts converting into gas. And where does the liquid is taking up the heat?
Sir, it is transferring into the mark or the human body.
Yes, it is taking up the heat from the human body and evaporating. And since it's a lot of heat, the nitrogen evaporates by taking heat from the human body, and this heat is such that the skin in the affected area gets frozen due to the sudden extraction of heat from that local point. As a result, the local area where the freezing process has taken place becomes very brittle, and it is easily removable. Clear? Point is clear or not?
Yes.
All right. So I'll stop over here.